you study real security incidents long enough, a pattern emerges that is both frustrating and instructive. The same mistakes keep resurfacing because boundaries are assumed to be stronger than they actually are.
Software is built on assumptions about input size, format, timing, and trust, and attackers succeed by violating those assumptions in ways developers did not anticipate.
These failures are not usually about clever math or obscure exploits, but about everyday data crossing from one context into another without sufficient skepticism. If you understand how and why these assumptions break, you start seeing common flaws as variations on a small set of themes rather than as isolated technical trivia.
That perspective is what allows you to reason about risk even when the exact vulnerability name or exploit technique changes.
One of the most foundational examples of boundary failure is the buffer overflow, which occurs when code writes more data into a memory region than was originally allocated for it. At the machine level, memory is just a contiguous space, and it does not enforce semantic boundaries unless the language runtime or operating system intervenes. When a program assumes that input will always fit into a fixed-size buffer, that assumption becomes an implicit trust boundary. If an attacker can exceed that size, the extra data spills into adjacent memory locations that were never meant to be modified by that operation. Historically, this has been one of the most dangerous classes of flaws because it operates beneath application logic, at a level where safety checks are rare, unless deliberately designed. The real danger of a buffer overflow is not merely that memory is overwritten, but that the overwritten memory can influence control flow. In many architectures, memory adjacent to data buffers may contain return addresses, function pointers, or other control structures that determine what the program does next. By carefully crafting overflow data, an attacker can redirect execution to code of their choosing, effectively turning input into instructions at the processor level. This is what enables arbitrary code execution, where the attacker's payload runs with the privileges of the vulnerable process. Even when modern mitigations like address space layout randomization and non-executable memory are present, logic flaws combined with overflows can still produce powerful exploitation primitives. The key idea is that once memory integrity is lost, the program is no longer behaving according to its design. Programming language choice plays a significant role in how exposed a system is to overflow risk. Languages that manage memory automatically, often referred to as memory-safe languages, enforce bounds checks and object lifetimes in ways that prevent many classic overflow conditions. This does not mean such languages eliminate all memory-related vulnerabilities, but they significantly reduce the likelihood that a simple input size mistake becomes a control flow hijack. In contrast, languages that expose direct memory management require developers to manually enforce boundaries, which is error-prone at scale. Over time, this has driven industry trends towards safer abstractions for new development, especially in security-sensitive components. From a risk perspective, language choice becomes a preventive control, not a guarantee, but a meaningful reduction in an entire class of failure. Another recurring boundary failure appears in structured query language injection, which happens when untrusted input becomes part of a database command. Databases interpret queries as both instructions and data, and problems arise when applications construct those queries by concatenating strings that include user-supplied values. When input is merged directly into the command text, the database engine cannot distinguish between intended structure and attacker-supplied syntax. This allows attackers to alter the logic of the query, bypass authentication checks, extract data, or modify records in ways the application never intended. The flaw is not that the database is insecure, but that the application violated the boundary between code and data before handing the query off for execution. The most reliable defense against this class of injection is the use of parameterized queries, which enforce a strict separation between command structure and data values.
With parameterization, the query is defined once with placeholders, and the values are bound separately in a way the database treats purely as data.
This prevents user input from changing the meaning of the query, regardless of the characters it contains. Input validation can still play a role, but it is a secondary control compared to structural separation at the database interface.
When parameterization is used consistently, entire categories of injection attacks become infeasible rather than merely difficult.
The lesson here is that secure interfaces matter more than clever filtering. Command injection extends the same idea beyond databases into operating system interactions. Whenever an application passes input to a system shell or command interpreter, it risks allowing that input to be parsed as executable instructions. This often occurs in utility functions that invoke external commands for tasks like file processing, backups, or system diagnostics. If user input influences command strings without strict control, attackers can append additional commands or alter arguments to achieve unintended effects. The vulnerability lies not in calling the operating system, but in failing to constrain how much influence untrusted data has over the invocation. Once again, the boundary between data and instructions collapses.
Path traversal is another expression of boundary failure, this time involving file system access.
Applications frequently build file paths based on user input, such as file names, document identifiers, or resource locators.
If the application assumes that input will always resolve within a specific directory structure, attackers can exploit relative path elements to escape those boundaries.
This allows access to files that were never intended to be exposed, including configuration files, credentials, or system resources.
The file system enforces permissions, but applications often run with broad access, making traversal particularly dangerous.
The underlying issue is trusting input to stay within an implied directory boundary without enforcing it explicitly.
Cross-site scripting shifts the boundary problem into the browser, where untrusted data is rendered as part of a web page.
When applications include user-supplied content in responses without proper output encoding, browsers may interpret that content as executable script rather than as text. This allows attackers to run code in the context of another user's session, inheriting their permissions and access. The application may believe it is simply displaying data, but the browser's interpretation rules create an execution context that the developer failed to account for. This flaw persists because it depends on how data flows from storage or input into different rendering contexts. Understanding how browsers parse and execute content is essential to preventing this class of vulnerability.
Cross-site request forgery exploits a different assumption, that a request sent by a user's browser is intentional simply because the user is authenticated. When a user has an active session, their browser automatically includes credentials such as cookies with outbound requests. Attackers can abuse this by causing the browser to send requests to a target application without the user's knowledge, often through embedded images or scripts on a malicious page. The application sees a valid session and processes the request, assuming intent where none exists. The flaw is not in session handling itself, but in failing to verify that a sensitive action was deliberately initiated by the user. This is another case where trust is extended too far across a boundary. Insecure deserialization is a more subtle boundary failure that occurs when applications accept serialized objects from untrusted sources.
Deserialization reconstructs objects in memory, potentially invoking constructors or methods as part of that process.
If an attacker can influence the serialized data, they may cause the application to create unexpected objects or execute code paths never intended for external input.
This vulnerability often surprises developers because the dangerous behavior happens implicitly during object reconstruction. The boundary between data representation and executable behavior becomes blurred, especially in languages with rich object models. Preventing this requires careful control over what types can be deserialized and from whom data is accepted.
Race conditions introduce time as a boundary that developers often overlook. These flaws occur when the outcome of operations depends on timing or ordering across concurrent processes or threads. If an application checks a condition and then acts on it later, another operation may intervene and change the state in between. Attackers can exploit this window to bypass checks or cause inconsistent behavior, particularly in file access, transaction handling, or resource allocation. The difficulty with race conditions is that they may not appear in normal testing because they require precise timing. Here, the failed assumption is that the world remains unchanged between two moments that appear sequential in code.
When you step back and examine these flaws together, the fixes start to look familiar, even though the vulnerabilities differ. Validation ensures that input conforms to expected shapes before it crosses sensitive boundaries, while encoding ensures that data is interpreted safely in its destination context.
Safe application programming interfaces enforce separation between data and instructions, reducing reliance on developer discipline alone.
Least privilege limits the damage when boundaries are crossed, because compromised components cannot access everything. These patterns do not eliminate all risk, but they dramatically reduce the likelihood that a single mistake becomes a systemic failure. The unifying lesson across all of these examples is that untrusted input is not dangerous by itself, but becomes dangerous when it crosses boundaries without sufficient control.
Whether the boundary is memory, a query parser, a command interpreter, a file system, a browser, or a timing window, the failure mode is the same.
Software assumes the world will behave nicely, and attackers prove that assumption wrong. As a security professional, your job is to recognize where those assumptions live and how they can be violated. When you train yourself to see boundaries rather than isolated bugs, you gain a durable way to reason about software risk that applies across technologies, frameworks, and decades of change.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.